Save this and share screen. Oops. Here we are. Okay, so virtual reality and augmented reality. Okay, so like I mentioned earlier at the beginning of this semester, I'm actually doing research in this area. How this VR, AR, or in general mixed reality can benefit civil engineering and the construction in the future. A good question to ask is when was VR, AR invented? Can anybody give me a quick guess when VR was invented?
2005.
2005. You'll be surprised. It was invented in 1965 by Professor Evan Sutherland from University of Utah. So at that time, they used this head-mounted device to simulate a virtual cube. And while you're moving ahead, so it renders different angles of the cube. So to give you a delusion that the cube is floating in the air. That was widely considered as the first generation of VR, as this is head molded, as this is the renderings changes with the angles of viewing. As you can imagine, because of the technology limitation, they used the entire room and a big mainframe computer to just generate a simple cube. And that's a picture from that time. See, they basically broke the ceiling tiles, and to have this one. And the device is so heavy, the users had to use the two hands to hold the hand-mounted display to see that. And I found this video on YouTube. Let me share also the sound of my computer. This is how it looks like. And this is the cube. And as you can see, you move away, you move around, you see this cube looks like you are surrounding a cube, but in fact, this is just a rendered picture. Make sense? So the computer will need to know where you are and where you are trying to see that virtual cube, and it changes the view of the cube, changes the render of cube. So everything was based on computation, not based on the real cube. And that's why VR is so difficult, right? So that is a 1968. Sorry, it's not 1965, 1968. And what the VR looks like today, this one is actually not very the newest. This is a video from 2016, but now you can see how VR has been advanced in 50 years. Sorry. So let me remind you, what you see here on the screen is not a real building. This is just a computer-generated virtual reality. But you check the light condition, you check the texture, and you can check the reflection on the metal. That everything is based on computation. Everything is based on the graphic card. See the reflection on the metal and also the laser. And you probably can tell something is strange because you cannot look outside the window. But it's still so real, and I think it can cheat if you put the VR goggle on, it can definitely cheat your brain. Actually, there's several years ago, there was a report by Accenture, the consulting company, I don't know why they published that report anyways. So they basically calculate that there is a 50% of chance that we actually live in a virtual world. We just don't know that. Let me fast forward, and they actually go to the bathroom, and you can see the mirror is also reflective, but you cannot see yourself. Here, you see the reflection. It looks so real, but then you will see there's no shadow, there's no reflection of yourself in the mirror at all. And then you know, oh, this is fake. Yeah, so this is you know, the state of art of VR, and you can imagine how much we improved from 1968, that single cube, to this kind of photorealistic renders of a VR world. I actually talked to the author of this video. I was so impressed when I first saw this video. I asked, he was an architect working in Paris, and he had some experience doing this computer rendering, and he just learned how to use Unreal. Unreal is a game engine, so we use game engine to develop VR and AR applications. So I asked him, how long did it take you to have this model? I was expecting some answers like a couple months, but he just told me about 2 weeks. So think about, you know, how much we can do within 2 weeks today to create this such a, you know, virtual world. Okay, so what is VR? This is the most widely accepted definition, you know, taxonomy of mixed reality in 1994 by Milgram, which we call the Milgram model. So basically it's a spectrum, you know, on one end is the real world, the real environment. On the other end is the virtual environment of VR. So the VR, virtual reality, is a pure 100% simulated world. So the VR goggle, you can tell there's no camera. So basically you are enclosed in a virtual simulation that you cannot see anything in the real world. So you're isolated in this virtual simulated world. But we also have something called augmented reality. So augmented reality means you have this goggle, but you can look through the lens. And so what you are seeing, most of what you are seeing is still the real world, like the real building, the real bookshelf, the real table. But then you see the virtual objects, computer-generated virtual objects overlay on the real objects. So that's called augmented reality. So augmented reality is a semi-open world that you have the simulated world as well as the majority is the real world. And we have something that is close to virtual reality here. Then you can imagine it opens a little gap for you to see through the world. So for example, Oculus Quest 2, the other goggle has an infrared camera that it's a VR, but if you double click it, you can just see the infrared view of the real world. That's called augmented virtuality. So it's closer to that 100% simulation of a fake world. Augmented reality is closer to the real world, but this is a continuous spectrum. So together we call this mixed reality or MR. So next time when you hear people talking about a VR, AR, MR, you know the difference. VR, once again, is a 100% isolated, purely simulated world. AR is 90%, 80% real world plus 20% virtual objects overlying on top of the real objects. And MR is the mix of them, okay? So actually, if you're using iPhone or maybe any kind of a phone today, you have really good AR applications, you know, like for example, IKEA furniture. If you want to see how it looks like in your apartment, you can open the app, just scan the floor, and it basically generate a virtual furniture and put it there. You can go close to it to see the details. You can go further away to see the arrangement. That is AR, okay? So VR, on the other hand, is HTC Vive goggle or Oculus, or PS PlayStation VR goggle, you wear it, but you should be very careful because you cannot see the outside world. That's VR. So talking about applications for VR and AR in construction, we are talking about a potentially big market. For real estate, that's $920 billion market. For construction, $1.2 trillion market in US. And the facility management, about a $640 billion market in the United States. And we start to see more and more practitioners and business and companies start to use VR and AR. And I have to say, for real estate, like for designers and for the sellers, they use a lot of VR. But for construction, for general contractors and facility managers, they actually prefer to using AR. The reason is AR allows you to see the real world, and this is more line up with the need for operational support, right? So for example, if I'm maintaining this pipeline, I do need to be able to see the pipeline and with added information such as insulation or the airflow. So AR is more adapt to that kind of application. But if you're selling some apartment, like luxurious apartment, I don't care if you need to see the real world, or maybe the apartment is yet to build, it's not there yet. So then VR appeal generation will be more suited. So this was an old prediction to predict the market share of VR AR in different industry sector on 2020. In 2020, so now we are 2020. We are at the end of 2020. I don't know if it's true in terms of the exact number, but the ranking is about the same. So the number one user of VR AR technology is still the video game. Of course we know. That's the force that a lot of companies are doing VR AR development. About 1/3 of the market is still video game, but a lot of people didn't expect that construction and real estate is the second largest user of VR and AR technology, about 18%. Or $6.3 billion market share of using VR and AR. And the healthcare industry is about 15% of that market. So anyway, construction and real estate is using a lot of VR AR technologies and will be growing fast in this area. So why bother? Why we should care about the VR AR technology in this AEC industry? So we talk about that. AEC is a highly fragmented industry. Have so many different parties, engineers, architects, customers, owners, general contractors, and we also talk about the fundamental source, the fundamental cause of a lot of issues in our industry is the lack of communication or the common understanding. A lot of times the designers design something and just wave the hands and walk away and give it to engineers. The engineers just added the structural design and mechanical design and then walk away and give it to general contractors. So there's a lack of common understanding, shared view, and communication. And according to the survey, about 50% of project cost can be waste. So if you're talking about $1 million project, maybe 500K can be waste, and about 30% of them could be solved with improved communication. So we still have 20% of product cost as waste and cannot be avoided. It makes sense, right? Because we are dealing a very uncertain industry, and unforeseen earth condition, shortage of laborers. Yes, we will have waste. Like I don't know exact number of bricks for this wall. It's based on estimate. So yes, there will be waste, but about 30% of the product cost are waste that could be saved with just improved communication. Like designers, general contractors, if they talk to each other, we can save 30% of the project cost. 56% of project cost is put at risk by ineffective communication. That's another survey study. The number is even more scary. And 1/3 of project failures are attributed to ineffective communications. Project failures are more than just a cost overrun, can be schedule overrun, can be unsafe behaviors, can be accidents, can be unsatisfied customers. So in general, 1/3 of the project failures we see can be attributed to ineffective communication. So why VR AR? Because it's a very good tool for us to communicate. And that's why we are switching from this. This is an old picture showing like how people were doing the design. This is what we call the studio, the workshop. But and we're switching gradually to this kind of immersive view of the building information. And also this picture shows that the people, the construction workers, were using augmented goggle. This is HoloLens 1, HoloLens goggle, to show the location of the bricks so they know where to put the bricks. So this is AR application for operation support, and this is VR for design and design communication. So we are doing that switch. And if you see the evolution of our industry, I see it as the information evolution. So if we say our industry is improving, is advancing, I have to say because we are advancing information. So from the original papers and drawing and pencils, that's 2D shapes, to building information modeling, it's 3D shapes plus more information, to VR, to AR. Think about that, guys. What are we changing? We are not fundamentally changing the way we build things, but we are fundamentally changing the way we share things, we communicate things, communicate information. So evolution of our industry is actually the evolution of information. Okay, so now let's talk about the applications, the benefits of VR AR technology in different phases of AEC. Let's say design. There's a concept called read or co-design. Think about that. I'm designing this building like a student housing, but the final user would be the students, but the students be able to share their thoughts, to share their expectation with the designer when the designer is doing the design? No, because like I said, this is a fragmented process. So there's a concept called co-design, which means we should bring the end user of a building to the original phase of design and share their insights, share their expectations. But the problem is we know the AEC can be very professional, and we cannot expect all the end users understand this or understand this. So professional drawings or models do not make too much sense to laymen. So that's the obstacle why this co-design concept cannot be realized. It just, and the users are not experts. They don't understand the drawing, the language we are using. So that's the first problem, that how can we make sense of a project so the layman, the regular people can participate in this design process. And also, project teams are often work remotely, right? So we probably have designers from California, we have users from Florida, owner from Florida, we probably have suppliers from Michigan. So the teams are working remotely. Can we have a very effective communication using Zoom? Probably no, right? So we can only share the screen to show things around. But if we can have an immersive way to bring remote members of the same project together, that would be a great addition. And also how we can coordinate design virtually. Like, yeah, I can have this Zoom meeting with designers, with engineers, with users, with general contractors, but I really want to see the same thing they are seeing. And it can be some model in front of us, so we can basically rotate the model, turn it around, and change things altogether. So we really want that kind of shared coordination of design. But that's still with the regular 2D drawing or even with building information modeling, it's still very difficult to achieve. That's probably why VR AR can play a role in the design phase. So let me show you this quick video from a couple years ago, from 5 years ago to be precise, while I was still at A&M. And we were trying to use VR, multi-user VR, to bring people, remote people together in the same VR model in an immersive way to coordinate design. So our first step is to convert a BIM model into VR, and we use the game engine. So the BIM model is kind of a Revit model. So we had this Revit model of this building. It's a Francis Hall, and we convert that into, I'm sorry. Oops, sorry. So that's a Revit model, and then we convert it into this VR. And this is, you can imagine it's kind of like playing a video game, and we have multiple users from different places walking in the same virtual Francis Hall, talk to each other, discuss the design using a ugly laser gun we designed at that time, as you will see. So we know, hey, how about that window? So we can talk to each other. It's kind of like a video game. Of course, we had this iPad version. You can pick your appearance, pick a avatar for yourself. And you can use the iPad to walk in the virtual building. Of course, we have this phone version. You can hook it up in this Gear VR or couple type of thing. And one thing we noticed that a lot of people, gray hair, construction company guys, they didn't know how to use keyboard and mouse to navigate themselves in VR. So we did some interesting thing. This is a V board. So you stand, there are 4 sensors below that. You stand on top of it just by leaning your body forward, backward, or jump. You could control the movement of avatar. As you can see, 2 of us were connected wirelessly. We were using the Wi-Fi, the internet to connect each other. And you can see here in the screen, actually there were 2 people. That was the 2 avatars for each of us. If I turn, they turn. If I walk, they walk. And we were using the old version of Oculus Rift at that time. That was still a developer kit. And we also built a video call function in VR.
Now follow me. Can you see this pointer? Yes, I can. Yes, I can.
And to make it more serious, we really want to exchange data between Revit, BIM, and VR in real time. So the goal was, if somebody changes the design in Revit, and a remote VR user could see the changes, in real time, and we did that. Like you change the size of this TV stand, and this is a real-time view of the VR user. It changes here, it also changes here in real time. We also tried some interesting thing, like this is a Google Doc. So if we change number in Google Doc, we could also change the size of the virtual objects in VR. Of course, you can use your phone to change the VR, and use one phone to change another phone, all cloud-based. All right. So we also have this virtual walkthrough using VR. Oops. As you can see, this is an information panel. Whenever you are looking at an object, it will show the information directly from a Revit model. You can also pick up things, move them around. Imagine you are using this immersive VR to design your own apartment. And you can walk, by swinging your arms. That's some code we developed. That's the information panel. You can go upstairs, don't go downstairs. And everything follows the physics. If you drop anything, it will basically fall on the ground, and it's physics simulated in VR. Like this, check this glass cup. Okay, so now imagine if you have this system, of course the design will be visualized, and the layman, the end users, can better understand the purpose of the design and also to put in their thoughts. Okay, so this is the system we developed at the time. So we call this co-VR. It allows up to 100 users to log on to the same server and navigate in the same virtual model in real time. Now imagine you have people, designers, engineers from different places, New York City, California, Florida, or even China, that you just tell them, if you need to have a meeting with them to talk about some design, you just say, hey, log on to this model 123. And everybody put on their goggle, they see each other, they talk to each other, they actually change things. It's kind of like play the video game, but it's in a very immersive way and for professional serious pieces. And this system we call it SoVR, synchronized VR. So, like you change something in Revit, in BIM, you can see the changes in VR in real time. And we used a really cool server, Google Doc. So Google Doc, at that time, we were thinking about, okay, so in order to exchange data between Revit and VR, we need a cloud server. But a cloud server is so expensive. We didn't have the budget to buy any server. So we actually found a cheap and high performance service, Google Doc. Google Doc is a word editor, but any kind of computer program is also, fundamentally speaking, a text, right? So our thought at the time is, can we program in Google Doc and use it as the cloud server to exchange information between Revit and VR? And the answer is yes. So this is what we did at that time. In Revit, each object has its own ID. So we basically just we wrote a plugin in Revit. So that thing will scan over the data in Revit and send everything and write everything as a Google document, a Google Doc. So with all the words. And then the VR goggle, we build in some kind of a program that will go to the web address of the Google Doc and read the right lines and the right paragraph, and then render the objects in real time. So let's say we push the data from Revit to this Google Doc 10 times a second, and the VR goggle will read the data from the same Google Doc 10 times per second. and render things around. In this way, we connect Revit and VR. And this is how it looks like. What you see as the 3D objects in Revit, this is how computer sees them. It's just lines of data, which we call metadata. So it shows the location of certain column. It shows the size of it. It shows the texture of it, for example. And so I will add in the tool we developed, will push all the words, the background metadata to a Google Doc like this. As you can see, this is how it looks like when we push the information from Revit to Google Doc. And it has a web address, right? This web address is unique. So the VR goggle will read this web address and go to the right line. Let's say go to line 12 and find the data point. See, you see all the data here? This process is called parsing, a way to clean up and abandon all the unnecessary information. So then in this way, we read the useful information from this Google Doc and render that in VR. This is how it works. Like in this case, you change the type of one chair, you see the immediate change in VR. In this case, you move the location of this column from here to here. You also in VR see the movement of that column. This is important, guys, because if you want to see, if you want to feel, if I make a design change by moving this column from here to here, you wouldn't feel that from the 2D design. So, but if you put the VR goggle on, you can see, oh, maybe if I move the column here, that will block the traffic. So that's not a good design. So we are 3D creators. We have to be in the 3D world to somehow feel the space and feel the constraints. And this is nothing new. People have been using this for a while, like McCarthy, in 2016, they did this hospital design. They invited the doctors and nurses to use a VR to see the design of the ward and the hospital rooms. Why this is important? Because they want their nurses and doctors to see how convenient the design is. Otherwise, if the building is done, and if they say, no, I don't want the bed to be here, I want to move the bed a little bit, it can cost them $500,000. Because you are not just moving this single bed, you're also moving all the systems connected to the bed, mechanical systems, right? IKEA, they also use the VR to enhance their design experience. So for example, for the kitchen design, one killer of their kitchen design is children experience. Because most designers, they are adults, they are always seeing the design from the adult perspective. So in this VR, they were able to shrink your body height. So for the first time, the designers were able to see the design from the view of a child. So they see, oh, maybe this cabinet design is not correct, the drawer design is not correct. So that's a innovative way, creative way of using VR in design. NASA, has always been using VR to design their control panels, because the astronauts are potentially facing very complex control panels, hundreds of buttons. So they want to see how they can improve that design. So they use VR to generate an immersive view of that. The DoD, this is Lockheed. They are also using multi-user VR to have mechanical engineers, electrical engineers, structural engineers come together in the same virtual space to design the engine. So they want to create a shared view of the same model and an interactive, tangible model so people can be more engaged in that design process. Okay, so let's talk a little bit more and take a brief break. Construction, so that's the VR AR used for design. And the AR used for construction, okay? So this is called isometric drawing. When we have mechanical construction, especially like a pipeline, it's impossible for us to have the 3D drawing. So we use this something called isometric drawing or ISO drawing to use 45-degree line, 135-degree line to show the pipes going forward, backward, going up, going down. You guys can feel the sense, right? We use the different degrees to show the 3D spatial orientation. But in order to imagine the 3D from this 2D isometric drawing requires something called visual spatial ability. Okay, and not everybody has the same level of visual spatial ability. This is something called a cube test. It actually tests your ability to imagine 3D from 2D. So let me ask you guys this question. You know, when this cube is rotated to this cube, as this cube is rotated to what? So this one rotates to this one is equivalent to this one rotates to what? A, B, C, D, E. Can anybody tell me the answer? Anybody?
Maybe D.
Which one? D as dog?
Yes.
Unfortunately, that's the wrong answer. Anybody else?
Is it B?
Yeah, B as boy, right? You know, because yes, you rotate this one counterclockwise by, let's say, 180 degrees, right? And if you rotate this one also counterclockwise by 180 degrees, actually B. See, that's basically, you know, it's not easy task for us to imagine 3D from 2D. And somebody tested the construction workers. You know, Gururam is a professor from Colorado State University. And so this cube test is standardized test, and the number, the final result is from 1 to 5. 5 means you have the most perfect visual spatial ability, and 1 means you are the low end of visual spatial ability. And we consider everything going above 3.5 to be okay for reading and understanding isometric drawing. But unfortunately, you know, he did the survey and found the majority of construction workers, their score of visual spatial ability actually going below 3.5. So this is actually very dangerous, guys, which means when we throw this isometric drawing to the construction workers, we expect them to understand their task, but in fact, the majority of them cannot understand that. So this is where VR can play a role. Howdy. So this is the new BIM with the VR function. As you can see, this part of this is my old facility at A&M. So this is a training facility, like, you know, when we teach construction worker the pipeline structure and everything facility, they use VR so they can see them instead of the isometric drawing. Of course, they can see the consequences of doing it the wrong way. And we also can simulate your body motion. So why this is important? So for example, you see you have a design, but from the 2D drawing, it's very difficult for you to tell if you have enough clearance to crawl in to maintain something, right? For example, above the ceiling, do we have enough clearance for me to reach my hand to a certain valve and turn it off? I don't know from 2D drawing. And it's also very difficult to tell that from even a BIM model, 3D model. So we have to be in there in an immersive way to try it out. But that involves we simulate the body motion. So in that way, I can tell if I'm blocked by something. So this is what we did. I just used a very minimum number of body character sensors, 2 sensors on my feet, 1 the waist, a head side, and 2 handheld controllers. That's 1, 2, 3, 4, 5, 6 data points. So using something called inverse kinematics, I can reproduce my body motion. Because I'm a human being, if the 6 points are moving a certain way, it's very likely that the body should move in a certain way. So I calculate that possibility to reproduce the body motion. Imagine that I could control this guy this lady, you know, to do some maintenance and see if there's enough clearance. And also for training, right? So we actually created this system that force you to walk on this plank, you know, from this building A to building B. And then we check, you know, your brain waves and your body motion to see that how this kind of unsafe behavior will affect your performance and function. And of course, we can also simulate your body motion. And this time we use something called a kidney camera. Based on the image of your body, we reproduce your body motion. Okay, and also VR can be used for quality assurance and quality checking. So in this research, we created a model for the same building. You know, this is Francis Hall. We created a VR model, but we intentionally changed 28 places. So imagine it's kind of like the construction didn't follow the original design. Then we put people in VR, ask them to review both the design and the real building in VR and see how that can help them check the discrepancies.
Getting twisted up in the darn thing. There we go. Cool. Thanks. Okay. Yeah, we definitely have not found 28 different discrepancies, but controller was missing a door here. They're getting twisted up.
And also VR for training. Like in this work, we create this drone simulator, and this is a real drone controller. We created an Arduino system that can capture the radio from the drone controller and send that signal to VR. So you are using a real drone controller to fly a virtual drone. You can pick the drone you want, and also the drone follows the real world physics, like it tilts, it rotates. And we also had this virtual iPad that is streaming the camera view from the virtual drone. I have a newer video here on my website. Once again, guys, if you are interested, you can always go to my website. You can just Google ICIC Live, ICICI Live, and you will see some more videos we have of our VR system. And this is actually the newer version of the drone simulator.
All right, Yummy, let's take off.
We simulated a construction site with different activities and noise. And also that you can hear when the drone is closer, the sound is bigger. You cannot see the drone, but you can definitely see that from the camera view, the view of the drone. It's over there. Also, this one simulates the wind effects. You know, when it's windy, the drone is shaking, moving randomly. Okay, and also, VR can also simulate a construction job hazards like a fire, explosion, and it's a safe place to train people how to react to different hazards and disaster. And we're actually working a lot with firefighters, Gainesville firefighters, College Station firefighters, Brand firefighters, and to see how VR can help them. But also, this can be a potential help to construction workers. Okay, so that's the VR application, for design and construction. So let's take a 5-minute break, and then we will be talking about how VR can help with the facility maintenance and operation. See you guys in a moment.